I didn't say anything important anyway. Far right-hand side, focus on looking at your alcohols and the carbonyls generated. That's going to be the easiest part. Okay. Initially, it may be difficult to track what alcohols make up an acetal, so go through the whole mechanism. Yes, it's long. Do it. Okay. By going through and doing that frustrating steps, you can start to get in the habit of finding out where all those pieces go, and you do better at it later on. Okay. Instead of just guessing your way through it. Okay? Questions on those? Okay. Talked about those. We also looked at why each of these reactions was favored, one direction or another. The last one versus the middle one, at the end of class, you guys kept pressing me, or I think, Jimmy, were you the one pressing me on this? On why the third one was favored to your products and the second one was not as favored. The primary driving force in that case has to do with everybody's favorite term, entropy. If we look at the second reaction, we've got 3 molecules going to 2. That is entropically disfavored. So entropy says, hell no, don't do it. If we go through and look at the third reaction, we start with 2 pieces that ends up with 2 pieces. So there is no entropic favoring or disfavoring. That kind of lack of disfavoring facilitates the formation of the acetal shown. The 5 and 6 membered rings are generally product favored, both because of this lack of entropy issue, and you have a nice stable ring structure formed out of it, okay, with our 5 and 6 membered rings. The reason this reaction becomes important is for this next aspect. We can use acetals by either making or removing them really quickly and easily. Well, we now have reversible chemistry. Reversible chemistry is nice because I can convert my carbonyl into something that is not a carbonyl and then go back the other direction, depending on what I wanted to do. Okay? So we can use this or reference this as a protecting group. For instance, if we started with, say, this carbonyl, and I wanted to get to this carbonyl. Okay. What happened? What type of reaction occurred? It's an addition reaction. Addition of what? Of H2. So not only is it an addition, it is a reduction. How do we reduce an alkene? What reagent do we add? Not borohydride. Borohydride is actually for nucleophilic addition. That'll reduce the carbonyl. What we would add would be H2 and platinum or palladium. H2 in the presence of platinum and palladium does reduce alkenes. It also reduces carbonyls. So if I'm trying to do just the reduction of the alkene, this reagent isn't going to work, and what I will end up with is the reduction of the alkene, but also the reduction of the carbonyl. Okay? That's a bit of a problem. Okay? So depending on how we designed our reaction, we may change our synthesis and say, okay, well, that reaction's not going to work. I'm going to have to go through and do an entirely different synthesis where I reduce the alkene, then I get my carbonyl. Okay? But maybe this is the only starting material you are allowed to work with. Okay? Well, under those circumstances, you have to do something to this structure to make sure that the reduction only happens to the alkene and not the carbonyl. So what can we do? We can get rid of the carbonyl. But if we lose the carbonyl entirely, we lose our yield. So what we try to do is convert it to something else temporarily and then reverse it so we get a relatively high yield back. So what do we end up doing? we break this down into 3 steps, where our first step is the introduction of our protecting group. Well, that protecting group really only reacts with our carbonyl. Okay. Now we don't have a carbonyl anymore, so what happens when I add the platinum and palladium? It reduces the alkene, and it leaves the other position, the acetal, untouched. What do I do to get my carbonyl back? I add water. Okay. The water addition on its own would go rather slow, so we typically add an acid to help push that along. Same deal back at the front. Okay. Because we have relatively low concentrations of the acid, we don't expect that to react with the alkene, and we can do our protection. We can then reverse that at the end by adding in a crap ton of water to push the equilibrium the other direction. And we've now done the full conversion. Protecting group chemistry, while important, is becoming less and less relevant in undergraduate environments. And the reason being is to do that single step, I had to do 3 different things. Well, 3 different things means more chemicals, more time, more manpower, more waste. All of those things are bad on an industrial setting. So what we would end up doing is changing how we would get to that final product so that we don't have to worry about doing the protecting groups. So you have to think differently about your synthesis to prevent the usage of protecting groups. So that is becoming more and more relevant as we look at chemistry in the future. For now, protecting groups are still possible. You got a lot of old chemists that's what they want to do. Okay? So you can fully expect to see these kind of questions of how to do those conversions and how to protect different functional groups from reacting. Make sense? Okay. Remember, what we're looking at is nucleophilic addition as a reaction, which means all we need is a polar pi bond. Well, if we take a look at a nitrile, what does a nitrile have? Polar pi bond. So guess what can happen? Nucleophilic addition. I did switch up the order of how the textbook presented this because in our previous slides what we were looking at was oxygen as a nucleophile. Well, in the hydrolysis of a nitrile, what's our nucleophile? Oxygen. Okay. It makes sense to me to group the nucleophile through with this. You'll notice that the chemistry is almost identical as our carbonyls. Some subtle changes occur. One of the big changes is you'll notice that the final product is shown in parentheses in both these cases. Why is it shown in parentheses? Nope. Nope. It's not reversible, no stereochemistry. What type of reaction happened in that second step? What happened in this second step? What happened in this second step? It does kind of look like a substitution reaction. But if we look at the reactivity of our starting material, in both cases the amide, okay, is it a particularly good leaving group? No. What's the primary chemistry in both the cases of the amide? It's the electrophilic carbonyl carbon, which means a nucleophile is attacking that carbonyl carbon, and we're doing what type of reaction? A nucleophilic addition. The pi bond is going to be the first one to break. But that doesn't get us to our final product. What happens? We reform the pi bond and we kick out a leaving group. So we end up doing a nucleophilic elimination. Why is it in parentheses? Have we talked about nucleophilic eliminations? No, that's why. Okay? That is in chapter 20 and 21. So what they are setting up in this case is the nucleophilic addition to generate an amide. That reaction will continue to go to do our nucleophilic elimination and take us all the way down to the carboxylic acid. Okay? You don't officially know that step of the reaction yet, so this is more like a forewarning, hey, watch out, something's going to happen. Okay? And we'll look at that reaction in a lot more detail in chapter 20 and 21. I don't remember which one it is, but it's in one of those two chapters. Okay?
How would you stop it at the amide?
You'd have to add a catalyst to prevent that reaction from continuing forward. So we can look at the acid hydrolysis of nitriles. You'll notice it's a very similar mechanism to what we've seen already. You have an acid. You need to neutralize the acid first. So we find the most available pair of electrons. Hey, nitrogen's got a pair of electrons. Nitrogen then becomes positively charged, just like our carbonyl carbon would have become positively charged. So in that first step, what we've done is activate our polar pi bond so that it can then react as a better, glad we were all listening, electrophile. So our weak nucleophile of water can now attack the polar pi bond, which breaks our pi bond. We've done our nucleophilic addition. We have to do a deprotonation because now water doesn't, or oxygen doesn't want to be positive. Same thing happened in our acetyl mechanism. Okay. We then look at our structure. We've got a double bond, and this is the interesting one to me, is that next product, this guy. Okay, that one's kind of a bizarre step because we look at that. That structure is neutral. When do we typically stop our mechanisms? When it's neutral. And yet, what does our textbook then go through and do? A bunch of extra steps to convert us to another neutral structure. Why do those proton transfers to take us to that other neutral structure as opposed to the one we started with? Why is it more stable? Oh, good call, actually. I didn't even see that. What functional group are we looking at? Roughly right there. You're looking very closely to something like an enol. What do the enols do? Tautomerize to our ketone. Good call. I did not see that at all. I was having a hard time coming up with a reason for that. So thank you. Okay. We have effectively a tautomerization here where we're just exchanging the location of the hydrogen. Okay. Why do we go through and do that? It is more stable with the carbon-oxygen double bond than it is with the carbon-nitrogen double bond. Okay. And we can determine that by looking at all sorts of other weird things. The one option that I was seeing, really what's changed is the hybridization on the oxygen. There's a sneeze somewhere in there. What's the hybridization on the oxygen there? Stop laughing at me and answer my question. sp3. Hybridization on the oxygen here. sp2. Which one holds the electrons tighter? sp2 holds the electrons tighter. Okay. Which element would we expect to have the electrons held tightest? Oxygen or nitrogen? Oxygen, because more electronegative. It makes sense for our oxygen to be sp2 hybridized. It's another little neat example on that. Though I like your enol suggestion better. Okay?
Well, maybe that's why it does the
It could be. I mean, you can run a similar argument with the keto-enol. Base hydrolysis, same idea. You add a base, the base reacts with the water, makes the water a better nucleophile because it's now hydroxide. Hydroxide now acts as your nucleophile and pushes the reaction through. Okay? Equivalent mechanisms as we've seen with the acetals. Okay. The only thing that's different is that now instead of it being a polar pi bond between carbon and oxygen, it's a polar pi bond between carbon and nitrogen. You'll notice that both mechanisms stop at the amide at this stage. Why do we stop at the amide? Because you don't know the other steps. Okay? So don't stress about the other steps yet. In 20 and 21, you can expect to see those pop up. But as far as this exam goes, we'll stop at the amide if you see questions on the base or acid hydrolysis of nitriles. Okay? Questions? Okay. This is actually kind of a nice segue, because ultimately what we're looking at for our difference in here is that we changed from an oxygen to a nitrogen. So guess what we're going to do on the next slide? Change from an oxygen nucleophile to a nitrogen nucleophile. Well, really, all we're trying to do is see what are the differences between our oxygen and our nitrogen. Okay, so what are the differences? Is there a difference in size? Nope, we talked about that. Within a row, we would say they are the same size. So there's really no size difference. One thing we could include on top would be lone pairs or electron availability. We'll say equals electron availability. Do they both have available electrons? Availability. Sorry. Yes, they do. Nitrogen has a lone pair. Oxygen has two lone pairs. They both have electron availability. Would we say that oxygen has more electrons available? That one becomes a trickier question. Yes, there's more lone pairs, but how many pairs can you donate at any given instant? One. Okay. So after we react it once, nitrogen is wiped out of lone pairs. Would the oxygen be able to donate the next pair of electrons? Let's pick something simple. Say NH3 and H2O. Let's donate electron, or have each of those donate electrons. I'd end up with NH4 plus, so I lost one lone pair. In the case of water, what do I end up with? H3O plus hydronium. Still has that lone pair. Is that lone pair donatable? No, because it's already positively charged. So even though there's two lone pairs, only one of them can do anything anyway. So we're still looking at the lone pair electron availability for both nitrogen and oxygen identical. There is no difference in size. Right? So that gets us to the next stage, electronegativity. Is there a difference in electronegativity? Yes. Oxygen is more electronegative than nitrogen. How will that affect the reactivity of your reagents? Right, let's pick something simple. Simple reaction. Say base strength. Which would be more basic, an oxygen or a nitrogen? Okay, this is fun. We get two different answers floating out at the same time. How do we evaluate? What is the definition of a base? Donates electrons. Do they both have electrons to donate? Is there a difference in size? So it's electronegativity. How is the electronegativity going to affect the base strength? What is the definition of electronegativity? The ability to hold electrons. Oxygen being more electronegative will be less basic than nitrogen. What about nucleophilicity? It's the same thing. Nitrogen is going to be a better nucleophile and a better base than our oxygen all the way through. Which means what we'll end up doing is taking the exact same reactions we've already looked at and we repeat them. Except now it's nitrogen acting as the nucleophile. And at every step of the reaction we need to say, nitrogen's a stronger nucleophile. Is this going to change how I looked at my reaction? So you get to make that decision. Quite literally. So we'll split it into half the class, or you can do it in groups of 2 or 3. Do not do that. for the nitrogen? Why does that second attack not happen?
Is it because nitrogen isn't as electronegative and it's more of a nucleophile?
Nitrogen is a stronger nucleophile than our oxygen. So what happens at that initial stage is that our nitrogen, let me clean this guy up a little bit. Whoa, go away. Our nitrogen can very quickly donate electrons in and kick out our leaving group to take us to the imine. And it is stable at the imine because nitrogen is a better nucleophile than our oxygen. The oxygen, on the other hand, can't go through to form that structure because it is not a good nucleophile. Nitrogen's chemistry is slightly different from that of oxygen. Better nucleophile, better ability to stabilize that positive charge.
With a partial positive on the carbon, nitrogen attached is less positive.
Is less positive, so we get less likely to have a second nucleophilic attack. So we end up stalling at the carbonyl equivalent at the imine. Kind of a neat little system. Okay? Do you guys want to take a moment to take pictures or anything? Okay. We just talked about that. So, we'll make this a quiz. You're following the same pattern that we did for all of your mechanisms. There we go. Imine. Next one, don't ask me to name it because I don't know how to name it, actually. I'm going to be honest. I think it's a hydroxyl imine or hydroxylamine, something like that. Next one, if we follow the pattern, how many of you put this answer? That's a really good first step. What's the problem with this structure? It's positive charge on the nitrogen. So what happens? You remove the second hydrogen from your carbon next door, and you get a little elimination reaction, and it's referred to as, ooh, geez, an enamine. Yep. Ene, like an enol, it's an amine, alkene, and an amine. It's our enamine. The last one with the question marks, you should have been able to come up with those reagents. You just need the missing piece. Whoops. The very last part that's really tricky is figuring out exactly what happens on that next one. And that is it. What the? Yeah, what we're looking at there is what's known as the Wolff-Kitchener reduction. Okay. What is happening in the Wolff-Kitchener? You go through and form that, whoops, ignore that can it be sped up thing. I don't care about that. You form your effectively enamine or imine structure. KOH is a really strong base. Deprotonates. Can pick up hydrogen from somewhere in the environment, usually water in this case. With more hydroxide. I didn't show any of the resonance stabilized intermediates, but you should be able to identify those. You would end up with nitrogen, triple bond to nitrogen. What happened to the bond between the nitrogen and the carbon? It is gone. Why does this reaction occur? Oxygen is not as strong a base as nitrogen. Why on earth would we deprotonate the nitrogen? What's that? N2, the final product, is incredibly stable. That's what drives the Wolff-Kitchener reaction. Hydroxide is not as strong a base as the nitride ion, if you will, that's formed as a pseudo-intermediate. But because I go through and form the nitrogen gas as a final product, that drives this reaction forwards. Right? And what we have is a reduction. On a personal note, I've tried to do this synthesis and failed awfully at it in the lab. I still don't know why. I blame it on the patent. Okay. But yeah, so that's our Wolff-Kitchener reduction. As kind of a preview of what we'll end up seeing, I don't care about the cyanide one. What we're now going to spend our focus on is this little section down in the corner here, the aldol reaction. All that's happening under the aldol reaction is that you are going through your keto-enol tautomerization to generate what? A carbon nucleophile, which can then add to your carbonyls. Okay. The tricky part is that when we go through and do our aldol reactions, most oftentimes they are self-aldols, meaning you only see one carbonyl compound. If you convert that one compound into an enol, you're like, well, what the heck does it attack? Remember, your reactions have billions of molecules. When you run the reaction, you're not converting all of it to the enol. You're converting maybe 1 out of 99. It can then react with the other carbonyls and continue through to your aldol product. Okay? That is the last part of chapter 18.